Okay.
Pointer.
Yeah, here, and this is forward. Sorry, this doesn't work.
Down. Maybe down.
Okay, I can just use the keyboard. Okay, good afternoon, everyone. So I'm very pleased to be invited here to introduce my recent work that has been done in the past couple of years. So today I'm going to talk about the thermal transport in advanced energy system. So I think lots of Phonons concept, the traditional concept of Phonons has already been discussed in the previous talks. And today I'm going to talk about some interdisciplinary study of the Phonons, so how to treat the thermal transport Phonons with some other heat energy carriers. So this is more about the fundamental or more frontier research about the Phonons and beyond the lattice vibration. So my name is Ming, and I'm from RWTH Aachen University in Germany. So I have a group there, and then my group is mainly focused on the micro nanoscale thermal transport of phonons and also the phonon other interface interaction. So about the background, everyone knows that the heat and heat transfer plays a critical role in many aspects of modern science and technologies, such as the thermoelectric. This is a very major, one of the major phonon applications. And the thermal management is widely used in, widely seen in lots of situations, the microelectronics. So in the recent years, and heat and heat transfer also be very important in phononics, very small scale device, or even very important in the biological system, because everyone knows that the biological system actually is not very efficient to transport heat away. And also even in the extreme conditions like high pressure, high temperature phase, and for example, like Earth's core conditions, which is very, very challenging if you want to do the experimental study, right? So all in all, so we know that a deep fundamental understanding of thermal transport in various materials, especially with different dimensionalities and different organ conditions, is extremely important for development of new generation energy systems. So my research is particularly focused on the micro nanoscale thermal transport. When we talk about this specific topic, we know that it is interweaving surface interface effect or non-confinement effect. So sometimes you can treat the phonons as traditional like particles sometimes you have to consider the wave nature of the phonons. For example, there are two major carrier directions in this direction. On the one hand, by miniaturization, if you make the structure smaller and smaller, so nanostructuring can make the heat dissipation to be more difficult, so that a very low thermal activity can be realized, so which is beneficial, of course, for high efficient thermoelectrics or thermal insulation. So in this case, you don't want the heat flow in the structure. But sometimes we do want the heat go through the material very quickly. So this is associated with high thermal activity for some materials or some low thermal resistance across the interface, which can be beneficial for the high performance heat dissipation in thermal management. So of course, you can do some treatment for the phonons, and you can manipulate phonons, and also take advantage of some phonon non-confinement effect. So when we talk about the interdisciplinary study of the phonon transport, we have to know that the energy carrier, majorly you have different energy carriers. So for example, molecules, if you have talk about the gas phase, and then the gas flow around or ping-pong-like movement, and then they can take the energy away. And the photons also can take the energy away, radiation, for example, right? And then the major heat carrier is the phonons and the electrons. So these two are major heat carrier. So in different materials, you have different situation. The pure metals, it's dominated by the electrons. Semiconductors and the insulators, the heat energy is transported is dominated by the phonons. So, in the recent study, so as nanotechnology develops, and then in most of the situations, you have to consider the phonon or particle-like behavior and coupled with some other basic carriers. So in that case, so actually, you have to introduce this interdisciplinary treatment of the phonon transport, so which makes the phonon transport to be more challenging and complicated. And then such case you can be found in lots of situations. For example, like photovoltaics, you have to treat the phonon interaction with the photons, and then phonons, the traditional treatment, for example, heat thermal management or some like heterogeneous structures, and the electrons can be widely found in some electronics devices, and then where you have to transport the electrons, electric conductivity, but you also have to care about the heat dissipation, and sometimes these effects couple with each other. So first, I will talk about the traditional phonons. I think this definition is well defined, and it's well known. We know that every material is composed by the molecules or by the atoms. And then if you talk about the structure of molecules, and then its atoms is composed by the nucleus, and then electrons just flying around, right? And then if you use a simple idea of the lattice vibration, so if you just remove the contribution of electrons, and then you can just get the traditional definition of phonons, because once you get out the electrons, you do not consider the effect of electrons, and then everything left is just this lattice. And then due to the temperature effect, and lattice will vibrate, and then we have the language of phonons, and then you have different modes and the mode conversion, and also the phonon scattering, phonon gas model, and so on, right? So this is the traditional definition of phonons. So heat is carried by the lattice vibration, and then that vibration in the terms of physics language, and then we use the phonons to describe this phenomena. And then you have many different properties of phonons. For example, you have the basic, very like a three phonon scattering or some other different type of three phonon scattering. You also can consider the phonon scattering of the interface, because you have different structure, different phonon dispersion curves, and different phonon properties for different materials. And then you have this similar picture, like treat the particle lag, or you have involved the phonon wave lag is also the same, right? So then you have many different phonon processes in the materials, phonon scattering, impurity scattering, boundary scattering, and so on, right? So then if you talk about the small scale, and then once the small scale, the size, it becomes smaller and smaller, and then all these phenomena will become different from the Barker-like. And then you can manipulate the phonon transport at the small scale by manipulating the phonon behaviors, right? So that's the traditional phonons. So my talk actually, so today I will give you some my recent study in the traditional phonon transport. So especially I will talk about some new approaches for high efficiency thermoelectrics. So there are some like new concepts we propose, and then we study how the phonons can be manipulated, which can be beneficial for high efficiency thermoelectrics. And then in the major part of this talk, I will talk about some frontier of the thermal transport. This is more about the phonons beyond the traditional lattice vibration. Especially, for example, I will talk about the phonons interaction with some other more complex interfaces or more complicated like dislocation inside the material. And in the last part, I will talk about more new concept about the electronic thermal transport, not just about the phonons, but we have to consider the effect of the electrons. Okay, so first let's talk about the traditional phonon transport in the energy conversion application. So this is related to the high performance thermoelectrics, as we were known that the energy problem becomes a global challenge in the 21st century. So everyone would like to save some energy, or we would like the society is very concerned about the energy sustainability and also the efficiency. As we also know that in lots of industry process, when we generate the electricity, especially, and actually lots of 6% of energy is wasted just in this high temperature gas. And also for if you drive the car, and then actually over 1/3 of fuel's energy is wasted in exhaust gas. So such energy, once it is repaired into the air, and then such energy cannot be used anymore. So then people realize that a commonplace understanding is that the more urgent demand for the high efficiency energy is needed. And then a very simple idea is to use the to take advantage of the Peltier seebeck effect to recover such waste heat energy and then transfer back into the electricity, so that we can use it again. So such actually this thermoelectric effect has already been produced into some like small device or some device level applications, and then we have widely used in some applications. For example, in the aerospace, so you launch some object into space, and then you cannot. So far, right now we get the electricity by the solar panel, but what if this object turns into the back, and then you cannot get the sunlight anymore? So how to get the sustainable electric energy? So the people think about a way to use the thermoelectric device, and then you can convert the waste heat, or not the waste heat. Actually, you manually introduce some temperature gradient, and then you can generate the electricity so that you can have the sustainable power supply there. And the thermoelectric effect can also be turned around, like switch back, and then you can realize the temperature gradient so that you can cool down something, right? So although it looks like a very promising, but the challenge is that the energy conversion performance is very, very low. So this is related to the Seebeck coefficient. So for example, the ZT coefficient is defined as the definition of this Seebeck coefficient and the electric conductivity divided by the thermal transport property and then times the absolute temperature. So although the formula is very simple, it's very challenging actually to enhance the ZT coefficient to be very, very large value. This is because the two terms, or the two major parts, one is the electronic transport part and the other is the phononic transport part. Actually, they are strongly coupled with each other. So this figure, this is a very typical figure. This shows that the Seebeck coefficient and the electrical conductivity, actually this is a function of free carrier concentration. They have this opposite trend. So it shows that at the optimal free carrier concentration, you can realize this S square sigma to be the maximum, so that you can maximize this power factor. But of course, in the meantime, you also have to consider the free carrier concentration, the effect on the phonon transport. But if you consider everything together, and then actually the whole study makes it very, very complicated. So actually, so far there is no 100% accurate method can predict this ZT coefficient to be very, very accurately from the fundamental science point of view. So far, most of the study, they just some part of study, they focus on the S square sigma. Okay, I just take a look at the power factor. I use some like a traditional model to treat the phonon transport, electron transport. But from us, for example, my expertise is focused on the micro nanosecond transfer, so we can accurately calculate the phonon transport part, but the effect on the power factor, so it's sometimes it's a weakness. So anyway, so if you want to enhance the ZT coefficient, you have to treat this coherently, but not just some individual term. So far, most of research, of course, is focused on how to reduce the thermal activity for the lattice part. This is because this is the only part of lattice do not have a strong dependence on the electronic structure. So in this way, actually, there are some studies focused on the different concepts. For example, the major concept is focused on the phonon glass electron crystal. So you can make the crystal structure to be very complex, and then so that the phonon scattering could be very, very strong, and then you can realize the phonon transport to be minimized, and then in the meantime, you can realize the electronic transport can be considered large. And then in the recent years, people also proposed another concept is called the phonon liquid electron crystal. So such order-disorder structure actually is also semiconductor-like, and then you can conduct the electrons very well, but in such disorder structure or order disorder structure, the mixture structure, you can expect that the phonon transport can be very, very low. That's easy to understand, right? And then both methods can be combined with the nano engineering. So you can make some device, you can make the bark-like and then to be the nano size, and you can make a nanowire, you can make the two-dimensional film, and or you can make a polycrystalline and nano structures, and then you can further reduce the thermal activity. But now the bottleneck of the thermoelectric is that how to decouple the electronic and phononic transport. This is necessary to enhance the ZT coefficient significantly, because as I just mentioned, so far most of research are focused on individually study the electronic and the phononic. But if you want to enhance the ZT coefficient significantly, you have to decouple these two. But of course, decouple these two actually is not very easy. It's not very easy task. So here we propose two new concepts to enhance this behavior and then to try to decouple the electronic and the phonon transport. So the first new concept is to use the negative thermal expansion material under the compression state. As we well know that the pressure is a very effective approach to enhance the power factor. This is what we're doing. For example, people have found that not only just through numerical simulation, but also through experiments, if you apply the pressure to the materials, and then you can easily enhance the power factor largely, for example, also for this material. But in the meantime, people also find that if you apply the pressure, the thermal transport property can also be enhanced. That's also easy to understand, right? Because if you apply the pressure, the atoms become closer, and then the vibration density of states and the vibrational, the phonon group usually enhances because the bonding becomes higher. And then it's also not good to just reduce it, right? So then the universal question is that, is it true for every material? So is it possible to find some material with negative pressure dependence? So here I'm going to show you that by you carefully choose some materials or some very small type of the materials that you can realize that under compression state, you can realize the thermal activity goes down, and in the meantime, you can realize the power factor goes up, so that you can let the electronic and the phononic goes in a different way, right? So that you can enhance the ZT coefficient. So our computational procedure is based on the first principles. We use the unharmonic lattice dynamics coupled with the BT calculation. So the computing procedure I don't need to repeat here, and I just want to say that of course this approach is based on the assumption that we neglect the higher order phonon scattering. We just consider the third order, right? So everything is the technique is mature, and then we use this technique and then to screen the material. And then fortunately we found that this is a typical example that the AB compound, so mercury telluride, we found this mercury telluride is very special. So the thermal activity, so here is the relative thermal activity change with the function of pressure. If you apply the pressure and then the thermal activity goes down quite significantly, you can up to, for example, a gigapascal up to like 1.5 gigapascal, thermal activity is reduced by more than 60%, so which is significant, right? So this behavior is quite opposite to the diamond, as I just mentioned that the normal trend is the thermal activity where it goes up if you apply the pressure, right? So now the things that why the mercury telluride is a very, very like special. So actually mercury telluride is also a very good thermoelectric material. Of course, this mercury and is toxic and then it's not good for the environment. That's a different thing. So now we have to understand that why it's so special. So first we have to calculate the thermal activity as a function of frequency. So we have to know that what's the major heat carrier phonon modes in the mercury telluride. So if you plot this one, and then you'll find that the majority of the heat is transported by the low-frequency phonons, acoustic phonons. That's true. That's also understandable, right? And the detailed analysis shows that actually the majority of phonon transport is contributed by the acoustic transverse acoustic modes. So it's the TA modes. And then we also have to link this transverse acoustic modes with the negative pressure dependence, right? So actually we found that, okay, so this is the dispersion. So you can find that, okay, up to about 1.2 terahertz, and then the thermal activity goes up to 80%. And then phonon dispersion curve just cuts as the two TA modes. And then we also link this with the negative Greenland parameter of the TA modes. We know that the Greenland parameter can characterize the phonon unharmonicity in materials. And if the Greenland parameter is so large, it means that the phonon unharmony is so strong, right? And we also know that some materials we do have negative Greenland parameter. So if the Greenland parameter is very, very negative or is dominated, and then the whole material will have the negative thermal expansion. Of course, we do find some materials, they have some negative thermal expansion over a certain temperature period. So in mercury telluride, actually, you also have the negative thermal expansion found in experiments at the low temperature around 50 to 100 K, and then you have negative thermal expansion. So here we also find that the negative thermal expansion is contributed by the TA modes. Once you apply the pressure, this negative thermal expansion, this negative gradient parameter actually even goes to the negative direction. So it means that the gradient parameter, the magnitude becomes larger, and then which means the Phonon unharmonics becomes higher. And then of course you have this very, very low thermal activity, right? Because tau is inversely proportional to the magnitude of the gradient parameter. So now we found that's the reason. So the reason is that for such a special material, if you find that if the transverse acoustic modes dominate the Phonon transport, and if you find that the negative thermal expansion, negative gradient parameter of such modes continuously decrease under pressure, and then you will have this negative pressure dependence in the thermal activity. So then, since mercury telluride has a different pressure phase, if you continue to increase the pressure, so now intuitive idea is to study the thermal transport at a high pressure phase, right? So what we talked about in the past is just the zinc blend phase, which is at the normal pressure, and then another phase is called the cinnabar phase at the high pressure. So of course, the structure becomes more complicated, and then the Phonon dispersion becomes more complicated. And then if you calculate thermal activity, and then you will find that the thermal activity will go down significantly, and then eventually you can calculate the CD coefficient can be around 1.4 at the room temperature. So this value actually is so promising compared to lots of some other available thermoelectrics experiments. So then the idea is that, okay, we'll just find the one special case. Yeah. Sorry.
Just previous page, yeah.
Yeah, this the dots is an experiment, and this is experiment. This is our numerical simulation. So this is after we consider the defects in the material, and then you can still find that you have some like a discrepancy. So the BTE will give you higher thermal activity evaluation, and right now we realize that there could be higher order Phonon scattering, higher order, and then contribution. So because in this BTE calculation, we didn't consider the higher order. So that's why it's higher. So now we are still working on this and then try to get it done and try to compare with experiment.
Can you explain what is the blue and the pink curves?
This one is for different phase. So this is for different phase, and then you have this x-axis, so this is a different direction.
Okay.
Yeah. Right. This one is for the zinc blend phase, this 3 for the zinc blend phase. And then have the high concentration, low concentration, and the high concentration gives lower, but it's still a little bit higher than the experiment. Yeah. So now we extend this idea to some other ternary or binary compounds, because if we just find one, yeah. Yeah.
TA modes have a large Grunheim parameter under high pressure.
Yeah.
Could you possibly explain why that happens?
What do you mean? You mean high?
Why TA branch is getting more enharmonic under pressure?
Of course, right now we don't know the fundamental reason, because you have to take a look in the electronic structure and then how the bonding is so special. But right now we only identify that the TA modes is so special, and we'll also take a look at some literature. Lots of literature said that the negative thermal expansion material, and especially for the TA modes, is dominant. And also the TA modes will have negative thermal expansion. It's very, very rare to find that the RA modes, this is the RA modes. Longitudinal acoustic modes, in most of the cases, they do not have the negative thermal expansion, they do not have negative gradient parameter. But the TA modes is so special. And also this mercury telluride is a very simple structure, it's like a blend, and then, we are still take a look at the fundamental reason why it's so. I just want to see that so far we are finding this phenomena, but the more detailed, like how we can use this one to search more materials, this more, is underway. So now we also study some other binary or ternary compounds. For example, this is CDSB. We also find a similar phenomena. So if you increase the pressure, so lattice compressing, increases, and then the thermal activity goes up a little bit and then drops down quickly. And this is a binary, and then you also have some other ternary compounds. Silver indium telluride or copper indium telluride, you also find a similar, right? You could significantly decreases the same behavior. So now we are also analyze this, and then we try to produce maybe from material design point of view, maybe we can produce some like criteria, and then to identify, okay, if you have a structure, and then identify some atomic index, and then you can say that in this material you can predict like you have negative negative pressure dependence. Okay, so next the concept is about the twin structure. So as I just mentioned that we have to, the final goal is that to decouple the electronic and the phononic transport, right? So now the second concept is to use the twin structure. So we know that the nano-twin structure actually is widely seen and is also widely explained in terms of enhancing the mechanical properties. Everyone knows that, for example, starting from 2003, and then there is a science paper, 2004, and a science paper, and they talk about the nano-twin structure in the copper, and then they can enhance the mechanical properties quite good. And then we also found that you can see that the electronic transport property does not change too much if you have nano-twin. So this is very, very promising, very, very exciting for the electronic, right? So then an intuitive idea is that how we can transfer this idea into the semiconductor. So then if you introduce the nano-twin inside the semiconductor or the thermoelectric material, and then if we can maintain the electronic transport, and then in the meantime, you can reduce the phonon transport, and then that will be fantastic, right? So we use a model system of silicon. We introduce a nano-twin inside the nanocrystalline. So you make a silicon to be a nanocrystalline. Of course, everyone knows that if you want to make a silicon to be a very good thermoelectric, first you have to nanostructure silicon, because thermoactivity of silicon is so high, right? It's not good. And then you make it a nano size, and then nano size itself is not enough. And then you have to put lots of like a nano-twin inside. And then with classical BT calculation coupled with the first principles, and then you can find that the Seebeck coefficient and also the electronic conductivity for some nano-twin structure is enhanced. And then in the same time, you also find that the phonon transport goes down. That's easy to understand because you introduce some like a boundary, right? Because the nano-twin is also a kind of boundary to scatter phonons. So then you can see that the electron part, the power factor enhances, and then the phononic transport decreases. And then actually you can decouple this. Of course, the detailed, yeah. We take the value from some literature, and then they just measure. This is silicon, and then we just take a look from literature. So we didn't consider the effect of this boundary effect. We just use some simple model to take a look at the boundary effect.
Value that you pick to
yeah, it's a constant value. Yeah, it's a constant value. So we take it from the bark, and then we consider this boundary effect and also this twin boundary effect, and by some mathematical model. And then we finally calculate the power factor. So the phonon part is by the classical MD. Yeah. You have questions? This comes to the next picture here. Is we found that the mechanism actually is associated with this high band degeneracy. So it's quite different from bark. This is the bark silicon. This is the bark silicon. You have degeneracy is just 6. If you decrease this is the thinnest one. This is TB1, 2, 3, 4. This is the different thickness, different periodic length of the nano-twin. Because you can also think about the nano-twin structure is some kind of a special super lattice structure, right? You have this AB and BB periodicity, right? And then you can find that as the periodic length decreases, and then the band degeneracy increase, and then you have very, very high value. So the mechanism is that although we have a relatively low this effect mass, but the band degeneracy is so high, so eventually, so the Seebeck coefficient enhances. So that's the mechanism.
But But in the standard superlattice, whatever increases the degeneracy also lowers the group velocity. Why here you don't have the trade-off?
You have to take a look at the whole this. You have to take a look at the whole things because the mobility is associated with this one and also this one, and yes, so it's hard to say. You directly just say that one factor. You have more than one factor there. So I think this is a deterrent mechanism. You can take a look at our paper, and then there are some formulas there, and then we analyze the different curves. So maybe we can discuss this later on in details and after the talk. So eventually you can play with the different concentration, doping, different concentration, and also play with the polycrystalline size, the green size, and the figure of merit. Eventually you can reach about like 0.5 at the room temperature and then 0.9 at the 1100 Kelvin. So this is the maximum CT coefficient can be realized for the silicon, and if you compare with the literature for compare with the experiments, and then this is the highest value we can reach for the bark silicon. So it's bark-like, but it's polycrystalline, and also inside the polycrystalline you can introduce this nanotwin. So recently with the same idea, we are working on the lead telluride, so the PBT, which is a very, very common, very, very used, very, very excellent thermoelectric material. We can, with the same idea, and then we found that significant enhancement in the CT coefficient. So to summarize the thermoelectrics, and then I just want to say that we propose some new concepts and mechanism for enhancing the energy conversion. So, for example, the twin boundary enhances the electronic transport through this synergy effect of low effective band mass and the high band degeneracy. And the twin boundary, of course, scatter phonons, and then the thermal activity also goes down. So the detailed study can be seen in our recent nanoscale publication. So now I will talk about the extension of the traditional phonons beyond the lattice vibration. So we know that the traditional phonons is established in the concept that we just neglect the effect of electrons, right? So just take the electron away, and then the rest is the nucleus. But everyone knows that the electrons is always there, right? So electrons inside the material, you cannot just simply take it away, right? So in this case, actually, you have to involve lots of interaction between the electrons and the phonons. So for example, interactions between the phonons and other energy carriers, like electron-phonon coupling, can be very important for the additive manufacturing process, right? If you use a laser, high energy laser, and then cut something or process something or heat it up or something, and then you have to take care of the energy transfer from the electrons, which is carried by the lasers, and then electron energy will transfer to the phonons. And thermoelectric actually basically also have this problem, right? They cover each other right now. Of course, no theory can explicitly cover this topic. And the photon interaction can be very important for the solar energy conversion. This has already, some work already done by some groups, and then they found that sometimes the phonons can assist the solar energy absorption. So which means that if you have a temperature, and then the phonon vibration can help the material to absorb more energy of these sonars. And then phonons can also interact with some like highly inhomogeneous structures. For example, the very common case is the green boundary, right? This is very common. And then in the recent years, people found that the dislocation, introduce dislocation inside the materials, and then you can reduce the thermal activity, but without significantly decrease the electronic transport, right? Which is very beneficial for thermoelectrics. And also heat transfer at the extreme conditions is also very important. For example, the very, very high electric field, or very, very high magnetic field, or very high pressure, high temperature phase, like the Earth's core conditions, which is very, very challenging if you do experiment, right? Or to realize a very stable heat flux. So today we are going to talk about some typical topics. For example, I will talk about the phonon interface interaction, and then I will talk about the phonon dislocation interaction, and then I will talk about the electronic thermal transport. So the background for the phonon interface interaction is comes from the interfacial thermal management, especially for the heat dissipation for the electronics. And the background I don't need to repeat here. So our final goal is to enhance the interface thermal transport because you have to cool down the electronics, right? So in the tradition of thermal transport, so only two materials in contact, and then you have A and B materials, and then heat generated from one side, and then it goes away to the other side. And then in this case, the thermal resistance is just the interface resistance as these two interfaces, right? So nowadays, with nanotechnology, you can easily fabricate a nanomaterials, so we call it the thermal interface material, so you sandwich it between. So then the thing is that is it possible to reduce the overall thermal contact resistance as well. So here we found that by carefully choose some materials in between, and then sometimes you by reduce the thickness of the material, and then sometimes you can reduce the overall thermal resistance. So this idea is the first we talk about. We studied this silicon carbide gallium nitride interface. We know that the high heat flux gallium nitride device is very, very popular for these HEMT applications, and also the near junction heat flux could be very, very high, several orders magnitude higher than the typical supercomputers. And then the heat dissipation problem is a critical problem for maintain the performance. So here we introduce the aluminum nitride, so which is also widely used in the gallium nitride fabrication. So by introducing a very thin layer aluminum nitride, actually the overall thermal resistance or the conductance can be enhanced by 45 to 55%. So the mechanism, of course, comes from the Phonon bridge like effect. So it's more like a similar idea as Professor Henry presented just half an hour ago. So we found that aluminum nitride, if you take a look at the vibrating density of states, the density of states of aluminum nitride happens to fall somewhere between the aluminum nitride, the silicon carbide, and the gallium nitride. So then actually the aluminum nitride can serve as a phonon bridge. So then the phonons, the energy comes to here, and then you can transfer to the aluminum nitride and then transfer to the silicon carbide. Of course, this depends on the vibrant density states. If the vibrant density moves into some other regions, and then of course this does not help at all, right? So you have to carefully choose the third material. Another example is to show that the mass gradient interface, because you can also make sometimes you can make a alloy-like interface, and then you can also make the mass gradient interface. So we use a model structure, and then we found that if you use a mass gradient interface, the thermal resistance can be reduced by 6 folders. So this is also the similar mechanism, and then you can use some method to analyze the mechanism. So we use our recently developed frequency domain decomposition method, and then you can decompose the heat flux as a function of frequency, and then you can take a look at the different interface and then what's happening there. And then the determined mechanism I don't have time to discuss here. I just skip this. So now I will quickly talk about the phonon dislocation induction. So we know that the dislocation is widely seen in lots of materials fabrication, especially for the gallium nitride device. So when you fabricate a gallium nitride device, and then most likely you will form different levels of dislocation at the interface and even inside, right? So then the question is that how the phonon transport will be affected by the dislocation. So then we also know that in the local structure of the dislocation, around dislocation, and then you have this phonon unharmonicity because the atoms is arranged in a different way, and then you have to expect the phonon unharmonicity, right? So then we use a very simple approach to study the dislocation, the phonon dislocation induction. We also know that in the literature we found that the thermal actually can induce this dislocation drag effect because of the phonon dislocation induction. And if you talk about the mobility of the dislocation, and then if you have a temperature effect, and then the dislocation at the final temperature, they move slowly than the low temperature. So this is called the thermal dislocation drag effect. And in the recent years, just a couple of years ago, and this idea has been used for thermoelectrics. So you can introduce the dislocation, just concentrate on the boundary of these grains, and then the dislocation can further decrease the thermal activity, right? And then without significantly decrease the electronic transport. So this science paper actually is also talk about the thermoelectrics. So you can use this idea to enhance the city coefficient. Of course, there are some scientific questions, and I don't need to repeat. So our model is very simple. It's just the PBTE. So lead telluride is a very good thermoelectric material. So now we just introduce a single isolated dislocation inside the material, and then we keep a hot part, cold part, and then there's a heat flux, right? And then by decompose the heat flux into different frequency, we found that the middle and high frequency phonons are affected, right? It goes down, but the low frequency phonons are not affected. So this is somehow is expected because low frequency phonons normally have low mean phase parts, and then the dislocation in this case actually, the isolated dislocation is something like a big point defect. And then you have just point defect, and then the phonons with no mean phase parts, and then they just pass away, right? So the same phenomena is also found by the equilibrium MD. So if we do another case of copper, have a single dislocation inside, and then this is a temperature time domain normal mode analysis, and you also find that the low frequency and high frequency part and the scattering rate will enhance, and the reacting time will go down. Okay, so this is summary for the phonon structure induction. So we have found that for the very thin interlayer, and it's possible to enhance the interfacial thermal transport by the non-confinement effect. And also for the phonon dislocation induction can be strongly affect the middle and high frequency phonons, but do not affect the low frequency phonons, which is not very, very good for thermoelectrics, right? And also in the last 10 minutes, okay, I will talk about the electronic thermal transport beyond the electron gas model. But we will know that when we talk about metals, everything is, when we talk about heat transfer in metals, and the heat is the majority is covered by the electron, right? That's clear. And people have found that this is there's a very, very famous theory called the free electron gas model, and plus BTE, and then you can have the thermal activity is proportional to the temperature and also proportional to the reacting time of the electrons, and then inverse proportional to the mass of electrons, right? But the thing is that the critical parameter here, the tau, we don't know. And also there is no accurate theory or precise that can precisely calculate this tau, right? So which is very, very challenging. But we do know that there are lots of processes associated with this. So if we want to calculate the tau, we have to calculate a very complicated process like a phonon electron coupling, or induction, or electron coupling, electron defect coupling, or electron some other holes, and so on, right? You have many, many different complicated situations here. So it's very difficult to explicitly calculate each term and then get the final this tau, right? So here we introduce our new concept. It's called the electrostatic potential oscillation. So without explicitly calculate each individual term of the electron scattering, we just introduce this electrostatic potential oscillation, and then we just regard the vibration of the nuclear ice, and then we introduce this electrostatic potential in the space. This oscillation induced by the electrostatic potential is because of the thermal vibration of the nuclear part, right? And then in the space, the free electrons can feel this electrostatic potential, and then this potential can drive the electrons. So it means that this potential can do some mechanical work to the electrons. So this is the basic idea. So then first we have to prove that we have to get the relationship between the atomic motion and this electropotential vibration. So it means that we have to prove that in space, the electrostatic potential oscillation should be induced by the vibration of this nuclear ice. That's very easy to prove. For example, we calculate the peak of this EPO and the electrical potential displacement, and we do the Fourier transform, and then we get the frequency dependent, and then you can see that this is the peak. And then we can also do the same thing for the velocity of the ions, right? And then we found that the peak overlap with each other very, very rare. So it means that once in the space, you have the electrical potential vibration, and then this exactly because of the thermal vibration of the nuclear ice. So I think this is very easy to follow. And then after that, we also found that if you have a different temperature, so you have a high temperature and then low temperature in different temperature region, and then we found that you have different electrical potential oscillation. So it means that once in some region you have a high temperature, and then in this temperature, the vibration of the lattice is very, very fast or very, very severe, and then you have the higher amplitudes of this EPO, and at the same time, you also have this vibration, this frequency, also very, very fast. So this gives us this concept, or the foundation of this concept. And then we can find that, okay, you have a higher temperature ranging, and then you have this faster electron potential oscillation. So then, based on that, we can run the direct non-equilibrium ab initio molecular dynamics. So you can run ab initio molecular dynamics. You can have a heat flux here from heat end, heat source, and the sink, and then you have the heat flux flow around, and then you have the temperature gradient. That's easy, right? Of course, right now we are doing the line equilibrium ab initio molecular dynamics to the pure metals, not the semiconductor anymore. So now we have the temperature gradient. Okay, that's easy to understand, but we have to realize that this temperature means the vibrational velocity of the nuclear ice, so metal ions. And then with this temperature gradient, in the meantime, you also establish another gradient for the electrostatic potential oscillation. So you have in the space, if you have a temperature gradient in the metals, and then you also have the electropotential gradient in the space. But you have to be very careful here. There's no net electron transport. Otherwise, you have the electroconductivity, right? But when we talk about the thermal transport in the metals, there's no net electron transport at all. So the transport of the electrons is still in balance. So there's no net electron transport away. So here we also identify that, okay, although you have the gradient of this electron potential oscillation in space, there's no net flux because the average potential is still the same along the system. So then with that, after some mathematical or the physical reduction, and then finally we can correlate the thermal activity of the electrons, electronic thermal activity with this gradient, this EPO, this gradient, partial U, partial N air, so this is a gradient, and also the electrons charge, and then this is the number of electrons here in this EPO vibration. And then this is the temperature gradient of the lattice. And then thermal conductivity, electronic thermal conductivity of some typical metals is compared with experiments. You can see that this is lithium, Be, magnesium, and aluminum, and copper. You can see that our simulation method agrees with experimental value very well. So it's within like a 5% error, so which is acceptable. And also you can compare with this blue one is the BTE model. So this is the electron gas model. As I just mentioned that in the classical electron gas model, there's a critical parameter is this tau, reacting time of electrons. You don't know, right? Then we just typically choose like a 10 femtosecond, which is very typical in experiments or in literature. And then you can find that some of BTE or the electron gas model can predict thermal activity very well, but some of materials cannot, right? For example, copper and this Be metal. And then if you choose this reacting time just as the 10 picosecond, 10 femtosecond, and then you can find a significant difference, right? But our model do not involve such calculation. We do not need this value. So we can directly calculate electronic thermal conductivity for the pure metals. Another interesting phenomenon is that we found that we can also calculate the autocorrelation function of this electron potential oscillation. And then we found that in space, actually, you also get this decay. We fear that this decay, this is the original data, and then we fill this with exponential decay. We found that this exponential decay will give you a characteristic time about 10 femtoseconds, which is very, very close to the reacting time of pure matters of electrons in pure matters, as in lots of literature they accept it, right? But of course, right now, we cannot prove that this is a real reacting time of electrons. So we just found that this is a very, very interesting phenomena, and we are still working on that. And just in case that if you have any ideas about this, and then we can have some collaborations, and I'm quite open for this. So we don't know. We are not sure this is a coincidence or just some other mechanism inside. Okay, so by the way, so to summarize this part, we have proposed a new concept. It's called the electrostatic potential oscillation. And it's based on this EPO concept, we calculate the electronic thermal transport by direct ab initio molecular dynamics simulation. And then we can calculate the thermal conductivity of some pure matters very, very well, and then agree with experimental very, very well. And in the recent days, and we apply this method to the very, very high temperature, high pressure phase of iron in the Earth's core conditions, because such as I just mentioned that such conditions cannot be easily done by experimental study, because you have to apply the very, very high temperature and the pressure. And so we are trying to explore what's happening there and how exact the thermal conductivity of irons at such extreme conditions. Okay, finally, I would like to thank my group teamwork and also the funding support from DFG and ERS. Thank you very much for your attention. I'm very happy to take your questions and comments.
Thank you very much for your instructive talk. We have time for a couple of...
On your idea of getting the electron relaxation time, one idea I've had, I never took the time to try it out, but I think you can make an appropriate correspondence between the way that we calculate relaxation times in molecular dynamics for phonons. You should be able to do the exact same thing for an electron. So if you, for example, for example, an ab initio MD simulation, right? You have all these electron energies that are outputted at each time step. If you track those in times, they should be fluctuating as the atoms are moving. And then if you pick a particular state and follow it in time, the fluctuation correlation time should probably correspond to the relaxation time for that electron. But I've never tried it. I just suppose that it would work.
Yeah, that's a very good suggestion. Could be, yeah, could be. The thing is that how we define this electronic energy.
So you're computing it at every time step in a DFT calculation. So you get the energies of every electron, pseudo-electron that you're modeling in the electronic structure. Okay. So the energies are recorded at every step.
Okay. Yeah, could be. Yeah. Okay. I will try that. We have tried the Phonon part. So we have even for the pure metals, we also try the Phonon part, and then we already get this reacting time for the Phonons. So there's no problem. But the electron part, and then sometimes it's very hard to define the electron energy, and then this is not the exact same as the Phonons, and then that's why we have not tried this. But yeah, you are right. Maybe this is a very good way to try it, and then we could try that. Yeah, thank you.
Sorry, I couldn't follow your definition of thermal conductivity of electrons. How did you define it?
This also defines on the, this, I think is related to another picture I have to show. I don't know if I have some curves here. I hope I have some. For details, I would say that there are lots of equations, and also the basic concept, we have to use this picture. So, and then there are some like mathematics. So you have the temperature gradient, and then you have this one part, and then the other part, and then you have to categorize how much energy transfer.
What formalism do you use to define your thermal conductivity? Do you use green Kubo? Do you use what
no? We just use this. We just use this model, and then we calculate the thermal heat flux, calculated by this one. I think there's another formula somewhere. because we also have to prove that this vibration density, we also have to prove that the energy carried by the electrons and then is equal to some other like oscillating energy. This is a very, very complicated process. I just, maybe
So
I
the spirit
need to
is
send
not
you the
NEMD?
papers because,
Is it the non-equilibrium molecular dynamics type of spirit?
no, it has nothing to do with the Green-Kuber. We don't use,
Non-equilibrium molecular dynamics.
yeah, this is non-equilibrium molecular dynamics. This is non-equilibrium dynamics, and the formula is figured out by ourselves, and it's something like a Fourier, but it's not a direct Fourier transport. So eventually we use this formula, and then we.
So what is your electron dynamics? How do you evolve the electrons?
Right now we are just simulating the pure matters. So the only critical parameter is this n. This n is the number of free electrons, the thermal excited free electrons in the system. So for example, like lithium, it's just one for each atom, because just one atom is flying around. Another two atoms is 2s and one s2, so it's just fixed. It's just circling around in the nuclei. So this n means the number of atoms, free electrons that is thermally excited and also contribute to the thermal transport, that also fear this oscillation of the gradient. So, and then for different materials, and then you have different number. So lithium is 1, magnesium is 2, aluminum is 3, copper maybe it's 4 or maybe 4 or 6 or something.
But you said you were doing ab initio MD?
Yeah, ab initio MD. This is
So
ab
your
initio MD.
electrons are on the Born-Oppenheimer surface and you move your ions? Is that what
Yeah,
it is?
yeah, right. This is done by VASP. It's just in the VASP, and then it's a car parallel molecular dynamics, and then you just run the dynamics, and then you can output the vibration of this lattice, and then the electrons. Of course, there is no explicit electrons, but you have the electron density, right? And then the atoms, the iron cores, can vibrate due to the thermal vibration, and then you have this part, and then you have the electron potential in the space. They change with time, right? Because this is the position, and then this is density, this is rho, this is iron, field iron, right? For example, for electron, this is 1, right? And then this is the potential induced by these irons. So in the space, you can imagine that the irons is the vibration, and then in the space, you have this electronic potential vibration. In the different temperature region, you have this different oscillation. So we have proved that this is a proof. You can see that this blue one, I think this is a displacement of these iron cores, and then you have this oscillation of the electron potential, and then you find that they are exactly the same, because once the irons is vibrating with a different frequency, and then this electron potential oscillation have the different frequency, right? So you have exactly the same frequency. So now we can prove that in the space you have the electron potential vibration oscillation, and then this is induced by the vibration of the irons, and then the electrons can fear this position change, can also fear this oscillation. That's why you have this electron potential gradient, right? So for the high temperature range, the atoms becomes like a heavier like movement, and then this oscillation is much faster and with much more like amplitude.
So, sorry, you don't have periodic boundary conditions?
No, no, we
Slabs.
don't. We just have this vacuum
So you
layer,
have
this
temperature
vacuum.
on the left and the right?
Yeah, right.
So do you see any voltage appearing at the two
No,
ends?
that's a different thing. That's what I emphasize, that there is no voltage, because even if you have the different like amplitude of this oscillation, the average speaking, and then its potential is the same. So you still keep the potential the same, so there is no net electron drive away.
Yeah,
Sorry?
I mean, you should
So
have-
no, there's no feedback effect. There's no feedback effect. So here we check that the potential, average speaking potential is the same, but only the difference is that the potential is oscillation. You can imagine that, okay, you have two oscillators. One is oscillated much strongly and also with much large amplitude, The other oscillator is vibrates slowly and also with a much smaller amplitude. And then the average is the same. So the ions, so the electrons cannot drive from here to there because there is no potential gradient, right? The heat is carried by this model. Where is it? It's by this model because of you have the temperature gradient and then you have the different the details I don't remember very clearly because this is there are lots of actually there are also some formulas associated with the picture, and then I think there are lots of formulas. Let me try to take a look. Yeah, so for example, we prove that some like this energy is equal to some energy, and also I think there are some other heat flux. Yeah, heat flux by this NMD, and then there are some formulas there. Yeah, so eventually, so I think if you maybe I can send you the papers, or you'll take a look at the papers, and then everything is inside this paper, and also in the supplementary information there. And there are lots of figures, and also the improvement and so on, and the size effect and so on. We did lots of work, and there for the pure matters. But of course, this model right now is limited to the pure models, because as I just mentioned, that there is a critical parameter here. It's this number. This is the number of free electrons that can drive away or can fear this one. If you talk about metallic, it's different. So for metallic materials, part of electrons can fear this oscillation, can take the energy away. Part of electrons cannot. But we don't know how much is this N, right? For semiconductor, and then N is 0. So there's no electron transport. There's no electron thermal conductivity, right?
Okay, more question? If not, let's thanks again our speaker.
Thank you.
I would like to remind you that there is a poster sessions after the coffee break. So please visit posters.